All right, so section 7.8, exponential models with differential equations. So oftentimes physical phenomena can be described by a differential equation. For example, problems involving radioactive decay, population growth, and Newton's law of cooling can be formulated in terms of an equation that contains a derivative, or as we know, a derivative, slope, or rate of change. So you have your growth and decay. Um, you have your growth and decay function. In many applications, the rate of change of the variable y is directly proportional to the value of y, if y is a function of time. So if you have dy dt, the proportion can be written as following. The rate of change of y with respect to time is proportional to y. The general solution of this differential equation is given by the following theorem. So if you were to separate this guy and integrate it, I'm not going to show the whole entire step, but basically you want to move over the y to be with a dy. So we're going to end up with 1 over y dy. And k, which is a coefficient, is going to be with dt. So we separate and we integrate. You end up with ln of y is equal to kx plus c. When you solve this for y, you take base e to both sides. So you end up with y equals e to the kx times e to the c. Now, obviously, e to the c is just c. And I know I just did kx. It should have been kt because it is a dt. Well, e to the c is just going to be c. So actually, it looks like I just did it, the whole thing. So you got y equals ce to the kt. So we don't want to have to do that every single time, especially when we get into logistic functions a little bit later. So it is a good idea to memorize the model theorem for exponential growth and decay. So if y is a differentiable function of t such that y is greater than 0 and y prime, or dy dt, is equal to ky for some constant, this is the general solution, right? And c is obviously going to be the initial value of y, and k is the proportionality, is going to be known as the proportionality constant. It is the constant that will be proportional to y. Exponential growth occurs when k is greater than 0, and exponential decay occurs when k is going to be less than 0. So the proof of the exponential growth and decay model that I just showed up here is supposed to go in here. You're more than welcome to rewrite it in there. All right, example 1. The rate of change of y is proportional to y. So as soon as they say that term, you need to understand that they are basically talking about the exponential growth and decay model. And then when t equals 0, y is 2. When t equals 2, y is 4. What is the value of y when t equals 3? Well, knowing that it is the exponential growth model, we know that we are going to be using y equals ce to the kt. This right here is a very important statement. Without understanding that statement is the exponential growth or decay model, you won't know to use that equation. And we need to solve for two things in this problem. You got to solve for c, and you got to solve for k, so that we can actually find the valid equation and then